Alright, so we were trying to find the fundamental limits of this problem of lossy compression of a memoryless source. Right, we have a memoryless source xn whose distribution is given to us. We are assuming that this is discrete, and the goal is to compress this to a k-length compressed sequence or code word such that we are able to reconstruct a version x hat that is close to xn. Right, and the way we measure closeness is through this distortion. And the goal is to design a compression scheme, a lossy compression scheme, for which the average distortion is less than or equal to d, and the rate, which is k over n, is as small as possible. Right. So for this, we looked at a random compression scheme and found the rate that we can achieve using this random compression scheme. And this was done by choosing a conditional distribution Px hat given x, satisfying the expected distortion between x and x hat being close to d. That's our target distortion. And if we chose any such distribution Px hat given x, we saw that the rate needs to be at least where it is, yeah. The rate needs to be at least the mutual information between x and x hat if we want the target distortion to be small. Right? So what we have basically shown so essentially if we choose a random code book which is drawn according to the distribution Px hat, and the rate is basically larger than the mutual information between x and x hat plus something, then expectation with respect to the code book, expectation with respect to x of the distortion between x, the source, and the reconstruction is going to be less than or equal to d. Right, so this is basically what we showed in the previous class. So let's focus on just this particular quantity inside. So there are two expectations over here. One is with respect to the code book that we've chosen, and the second is with respect to the source. And we've deliberately designed the code book so that it is independent of the source. All right. So here's a question for you. Let's forget about what this means exactly for now. But let's say I have a random variable. So given, let's say a p x hat or some random variable c. In this case, the c corresponds to our code book. And you have some function of the code book, some function of this random variable c. All right? And you know that the expected value of f of c is less than or equal to some number, f bar. Okay. So I'm looking at a very abstract setting where I have some random variable c, a function of this random variable f of c, and somehow I am able to show that the expectation of f of c is less than or equal to f bar. Then I claim that there is at least one value of c, some realization of c, such that f of c is less than or equal to f bar. Do you agree with this point? Question? So there's some random variable c, right, drawn according to distribution Pc. And I'm looking at a function of this random variable f of c, some real valued function of this random variable. And I know that expectation of f of c with respect to c is less than or equal to some number f bar. Okay, f bar is some number. Then I claim that there is some realization of c for which f of c is less than or equal to f bar. I mean, that should obviously happen, because if for all realizations of c, if f of c is strictly greater than f bar, then the expectation of f of c should also be greater than f bar. Right? So what does this imply with respect to this statement that we had earlier? We showed that expectation of the average distortion, when we take the expectation with respect to the random code book, this quantity is less than or equal to d. So it must mean that there is at least one code book for which the average distortion is less than or equal to d. All right. So there exists a code book of rate r, which is arbitrarily close to the mutual information between x and x hat plus delta of epsilon plus little of 1, such that the expected value of the distortion is less than or equal to d. All right. Remember that our goal was to show that there is at least one code book for which the distortion is less than or equal to d and the rate is something. And the way we showed this in the proof was that we picked a random code book and showed that the average with respect to both the source as well as the code book of the distortion is less than or equal to d. So it means there is at least one code book for which the average distortion is less than or equal to d, as long as the rate is arbitrarily larger than the mutual information between x and x hat. So this is an example of what is called a probabilistic method. So we don't know how to explicitly construct a code book and analyze the performance of that particular code book. So what we instead do is we try to prove the existence of a good code book that satisfies, that has all the nice properties that we want. I can't pick one good code book for this particular problem. But if I take a code book completely at random, I know how to analyze it. And what this says is that there is at least one such code book, or at least one good code book for which the distortion is small and the rate is close to the mutual information between x and x hat. Right? And this is a very common technique that is used in information theory. Right? We did this also when we talked, in a sense, when we talked about fixed length source coding. We didn't know what is a good code book for compression, for fixed length lossless compression. So we chose a suboptimal one. In this case, of course, we're choosing a suboptimal codebook, but I don't even know how to pick an explicit suboptimal codebook. In the context of fixed length lossless compression, we chose the typical set as the codebook for compression. In this case, I don't even know how do you describe all of the code words in this codebook. In fact, it turns out that choosing a good codebook for a particular n is not easy. It's a very, very hard problem. We don't know how to do that for a given n. But even though we don't know how to construct one good codebook, this basically says that if I pick a random codebook, it is going to be good. In fact, you can go one step further. You can also show that most of these codebooks are also going to be very good. So if you pick a codebook at random and try to find out what is the probability that the codebook that you chose gives you a distortion less than or equal to d while having a rate close to the mutual information, it turns out that that probability over the random choice of codebook is actually very, very large. It's very, very close to 1. All right. We'll also revisit this particular technique when I talk about channel coding. There as well, we'll pick a random codebook and show that whatever the probability of error is going to be small for that particular random codebook. And we'll use that to show the existence of a codebook for which the probability of error is small. All right. And this is a very useful proof technique that's used not just in information theory, but many other areas in communications and computer science.
So in case of fixed length
Correct.
compression, we use typical set.
Correct.
But right now, as a variable length lossy compression, we don't know the size of the codebook.
So in this case, we're dealing with fixed length lossy compression, right? We're not talking about variable length lossy compression here. The problem with variable length lossy compression is that, okay, so there are two things here. One is, you could say that the k over here, let's go back to the lossy compression problem. One could say that the k over here could potentially be varying with the realization of xn, and you only want the expected value to be equal to r. Expectation of k should be equal to r, and everything else remains the same. Now note that whatever we have done so far, we have designed a fixed length lossy compression scheme. The rate that you can achieve using this fixed length lossy compression scheme can also be achieved using a variable length lossy compression scheme, right? Because in expectation, you want the rate to be equal to r. Now I'm fixing the rate to be equal to r all the time. So the variable length lossy compression in that sense would be a generalization. All right. But the natural question then is, if I allow this length to be variable, then is it possible to achieve an even smaller rate? And it turns out that the answer is no. You can't really do much better. This is really the best that you can hope for, even if you look at lossy compression schemes. Right? But we will not really discuss that in the course. Any other questions? Okay. So far what we've shown is that it is possible to achieve distortion less than or equal to d at a rate close to mutual information between x and x hat. Right? This epsilon can be made arbitrarily small, so you can get arbitrarily close to the mutual information. Right? But is this really the best that you can possibly hope for? Is it possible to achieve a rate even smaller than this? And also, in this case, we chose one particular p x hat given x. For every p x hat given x, you can achieve all of these guarantees. Right? So naturally, the rate you can try to achieve a smaller rate by choosing a better p x hat given x, because different choices of p x hat given x could give you different rates for the same, for x hat that achieves the same distortion. Right? So what is the best rate of compression? The best rate of compression is equal to this quantity that I call r star of d, which is called the rate distortion function. So the minimum rate of lossy compression for a given distortion d is equal to the minimum over all possible distributions p x hat given x, such that the expectation of d x hat, where this expectation is taken with respect to the joint distribution px hat, which is px hat given x, of the mutual information between x and x hat. Right? Because I can choose, I know that if I choose a p x hat given x for which expectation of dxx hat is less than or equal to capital D, and the rate is greater than ixx hat, then I can satisfy my distortion constraint. All right? But it turns out that you can't do any better than this. That is, if you choose the rate to be any smaller than r star of d, then the expected distortion should be greater than capital D. Or equivalently, for any coding scheme, for any compression scheme, such that the average distortion is less than or equal to capital D, the rate should be greater than r star of D. All right. So we'll see a quick proof of this. To prove this particular statement, I'll need the following result, which I'll leave as an exercise. So this r star of d is a function of capital D, right? And the claim is that r star of d is a non-increasing function of d, and it's also a convex function of d. All right. And the fact that it is non-increasing is slightly easier to see, because how does r star of d depend on capital D? It basically depends on capital D through this this expectation constraint, right? And if you increase d, if you take a d prime that is larger than d, then this constraint set only becomes larger, right? So you're minimizing over a larger set, which means that the minimum can only be smaller. So that's why r star of d is non-increasing in capital D. All right? It requires a little more analysis, but you can think about it. The second is how do you prove that it is convex in D? So one thing is, if you look at the mutual information is basically this is a function of px x hat, or if I write it out explicitly, I can write this as a function of px and px hat given x. Right? Now, if I fix a particular px and I vary px hat given x, because px is determined by the source, we don't have any freedom in choosing px. But if I look at this as a function of px hat given x, because px hat given x determines this expected distortion, right? If I look at this as a function of p x hat given x, then this is a convex, the mutual information is convex in p x hat given x. Right? We showed this sometime in the beginning of the course, right? So it requires a bit of a proof, but basically the convexity of r star of d follows from the convexity of the mutual information as a function of the conditional distribution p x hat given x. All right. So let's try to use this to prove that the mutual information is the best possible rate for lossy compression. And again, we'll use a very information theoretic proof of this particular statement. In other words, this lower bound will purely involve all of the various inequalities that we have seen in the first part of the course. So the main tools in all of these are basically the same thing. We'll use the chain rules of entropy, mutual information, and so on. We'll use some version of either Fanos inequality or data processing inequality, and essentially clever bounds on the entropies and mutual information. Okay, and always in such whenever you're trying to prove such bounds, so this is an example of an impossibility result. You want to show that if you try to achieve a certain distortion, it is impossible to achieve a rate that is below the mutual information, right? So let's take the quantity nr. The first step is always to express this in terms of an entropy or a mutual information. All right. So nr is going to be greater than or equal to the entropy of Ck, right? Because K is basically nr. There are nr bits. You don't know the exact distribution of Ck. But then when is the entropy of Ck maximized? By the uniform distribution. And what would be the maximum entropy? And what is the cardinality in this case? Cardinality is 2 to the power nr. So log of 2 to the power nr is just nr. Right? So this is basically restating that the entropy of Ck is the largest when Ck is a sequence of IID Bernoulli half bits, and that maximum entropy is nr. Right? Okay, so this is h of Ck, which is equal to the mutual information between, or let's write this out, this quantity is greater than or equal to h of Ck minus h of Ck given xn. Why is this true? Entropy is always non-negative. So h of Ck given xn can only be greater than or equal to 0. Removing a non-negative quantity can only reduce the amount, reduce the quantity itself. Right? This is equal to the mutual information between Ck and xn. Okay. So now I claim that this is greater than or equal to the mutual information between xn hat and xn. Can you justify this particular statement? Okay, and why can I use the data processing inequality? Yes, so remember we have xn, which is encoded to give you Ck, and purely from Ck you decode to get xn hat. So So xn, ck and xn hat form a Markov chain. So by the data processing inequality, the mutual information between xn and ck can only be larger than the mutual information between xn and xn hat. So by the data processing inequality, this is greater than or equal to the mutual information between xn hat and xn. Okay. Now, let us now use the chain rule of mutual information. All right, I'll write this as summation I equal to 1 to n, the mutual information between xi and xn given xn hat given x1 through xi minus 1. Okay. I claim that this is equal to summation I equal to 1 to n of the mutual information between xi and xn hat given xi minus 1 plus the mutual information between xi and xi minus 1. How would you justify this particular step? I've done nothing here except add the term mutual information between xi and xi minus 1. Equivalently, I am saying that the mutual information between xi and x1 through xi minus 1 is equal to 0. Yeah? Independence, right? We are assuming that the source is memoryless. That's an important assumption that we have made. So xi is independent of x1 through xi minus 1. So it's a memoryless source. I can add this quantity which is equal to 0. All right. Now I'll again use the chain rule of mutual information, which says that mutual information between x and y given z plus mutual information between x and z is equal to mutual information between x and yz. So this is summation I equal to 1 to n of the mutual information between xi and xn hat xi minus 1. Which is equal to the entropy of xi minus the entropy of xi given xn hat xi minus 1 why is this statement true? So basically I'm saying that this quantity is greater than or equal to this particular quantity. Because I mean this quantity is the same in both. This term is the same for both. So this is greater than or equal to this because it has a negative sign. Why is this true? Conditioning can only reduce entropy, right? And here I'm conditioning over more random variables. Here I'm conditioning only with respect to xi hat. So this is equal to summation I equal to 1 to n, the mutual information between xi and xi hat. So this, now remember, each of these, this is some function of the joint distribution between xi and xi hat. All right. So this is greater than or equal to summation I equal to 1 to n of the min of the mutual information between xi and xi hat such that, let me use a different variable for this, mutual information between yi, or mutual information between y and y hat and the minimization is taken over all possible p y hat given y such that the expectation of d y hat is less than or equal to this particular quantity, the expectation dx xi hat. So this quantity over here is some function of the joint distribution between xi and xi hat, some function of p x hat, right? xi hat. Here I'm taking the minimization over a bunch of distributions. I'm taking the minimum of the mutual information, which is the same quantity, but over a larger class of distributions, which also includes pxi hat. Right? So if you look at the set of all py hat, for which the expectation of dyy hat is less than or equal to expectation of dxi hat. Let's look at all possible pyy hat that satisfy this constraint. This set includes pxi hat. Do you agree with that? It includes pxi hat. But potentially it can also include other distributions. I don't care how many more distributions there are, but it at least includes pxi hat. So it means that minimum of the mutual information over this class of distributions should be less than or equal to the mutual information for one specific distribution in this class, which is pixi hat. Right? But this is by definition equal to R star of d and in this case D is just expectation D xi xi hat. Because by definition R star of D is minimum over all P y given y hat of expectation D y hat less than or equal to D of the mutual information. This is equal to n times 1 over n times summation I equal to 1 to n R star of expectation D xi xi. I've just multiplied and divided by n. Okay? But if you stare at this particular quantity, this is a convex combination of R star of some things, right? And we've just seen that R star is a convex function of the arguments. So a convex combination of the function is going to be greater than or equal to the function of the convex combinations. Right? That's by definition of convexity. So this is greater than or equal to n times R star of the whole convex combination going inside. Right? But what did we want? We wanted the average distortion to be less than or equal to capital D. That's our goal. Right? So this is greater than or equal to n times R star of D. Because this quantity can only be less than or equal to D, and the rate distortion function is a non-increasing function of the argument. So this quantity is greater than or equal to n times R star of D. So basically what we've shown is that if we want this quantity to be less than or equal to D, then the rate should be greater than or equal to R star of D. So this basically shows that it is impossible to go any below, to achieve any rate that is strictly less than this rate distortion function. Any questions? It was a sequence of steps, and it's fairly easy to justify each step. Requires a little bit of thought, but that is still easy. Getting the whole proof requires you to maybe look at the proof again and again. It basically is a matter of practice more than anything else, right? But throughout, this approach is the same everywhere in information theory. You always use the same set of tools, right? The goal is, in general, the formula is always the same. You typically start with the rate, express that as some entropy, and expand that out either using some set of inequalities to get some kind of a mutual information, and then use data processing inequality or Fanos inequality in some particular step. And usually through a sequence of steps, you try to bring it down into an expression that looks like this. So an expression summation I equal to 1 to n of some kind of a mutual information between only xi and xi hat, or some entropy of just xi. So essentially here we had, so the first sequence of steps was to show that the rate, n times the rate, is greater than or equal to this mutual information between two vectors. All right, and all of the rest of the sequence of steps was to show that this is greater than or equal to the sum I equal to 1 to n mutual information between xi and xi hat. All right, and this is usually the most sort of elaborate step, involves most number of steps. All right, remember that if xn hat had IID components, then this would essentially be equal to summation I equal to 1 to n mutual information between xi and xi hat. Just using the chain rule, you could just prove that. But in this case, xn hat are much more complicated than that because they are not IID. Remember that xn is an IID sequence, but then how do you get xn hat? By encoding and decoding xn. And this encoding and decoding process introduces correlations. So the components of xn hat are in general not going to be IID. They're going to have a much complicated distribution. It can be anything depending on the choice of the codebook. All right. But you can, just using the properties of the encoding, decoding, and basic information inequality, show that this is greater than or equal to the sum of the mutual informations. We didn't show that this quantity is equal to this. We showed that it is greater than or equal to the sum of the individual mutual informations. And usually once you have an expression of this sort, the rest of it is also fairly simple. All right. Okay. So basically what we have shown is that the minimum rate of lossy compression for a target distortion D is the minimum overall Px hat given x hat less than or equal to D of this mutual information between x and x hat. Right? So let's try to evaluate this rate distortion function maybe for a couple of examples. Okay, but maybe even before I go to that, I will just state the main result for, so far we've assumed that x and x hat are discrete alphabets. Right? X is a discrete random variable, x hat is also a discrete random variable. But all of this extends even when x is a continuous source. Because in practice, that is the scenario that we are most interested in. The source could be some kind of a signal. Like typically in a communication system, you would first sample a particular signal, a continuous time signal, and the sampled signal is quantized, which is basically lossy compression. Right? So for continuous dxn, which we'll assume to be memoryless with a density fx, r star of d. So right now we are assuming that x and x hat are both real random variables. This happens to be the minimum over all f x hat given x. So this is a conditional density for which expectation dxx hat is less than or equal to capital D of the mutual information between x and x hat. Alright. So in both cases the expressions are essentially similar, except that you replace the PMF with a probability density, a conditional PDF. Alright. But how you evaluate these and how do you design a code book can potentially vary. Alright. So let's see some examples, some concrete examples on how to evaluate this particular rate distortion function. Because remember, the rate distortion function itself involves a minimization problem. Right? So in general, there are two ways of evaluating the rate distortion function. The most general way is, of course, you try to solve this minimization problem using Lagrange multipliers or some constrained optimization technique. But in many cases, there is usually a simpler way to do it, which is basically uses tools from information theory itself to look at this. All right. And many of these involve guessing what the solution should be and showing that that solution in fact achieves this particular minimum. Okay. So let's take some examples to see how that works. So let's take a Bernoulli P source. So I have a sequence of Bernoulli random variables, and the distortion is basically the so-called Hamming distortion, which is equal to 1 if x is not equal to x hat, and it's equal to 0 if x is equal to x hat. So if I take two vectors xn and xn hat, dxn xn hat is basically the number of locations in which xi is not equal to xi hat. All right. So for this, r of d star becomes r star of d. This is the min So in this case, what is expectation of dxx hat equal to? Remember that x and x hat are both binary random variables, right? And dxx hat is equal to 1 if x is not equal to x hat and 0 if x is equal to x hat. So what is expectation of dxx hat going to be equal to? Something in terms of an event, right? It's the probability of some event.
Probability of the event where x is not equal to.
Correct. So it's basically the probability that x is not equal to x hat. You can't really say that it is 2p into 1 minus p, because remember that you don't know what is the relationship between x and x hat. They could be arbitrarily jointly correlated with each other. All you know is that x is Bernoulli P. X hat need not be Bernoulli P. It could follow some other distribution. It could be Bernoulli some Q. All right, the marginal. And the joint distribution could also be something more complicated. But nevertheless, the expectation of dx hat is equal to probability that x is not equal to x hat. All right. So let's look at this. So I want to find the minimum of this particular mutual information with subject to this particular constraint. So I'll do the following. I'll first try to guess a solution and then prove that that is in fact optimal, that it achieves this minimum. Okay. To do that, I'll say that x hat is equal to x plus z. Okay, that's going to be my guess, where z is going to be Bernoulli D. All right, let me see if that's the right choice. Okay, sorry, it should not be this. I guess it should be right. Okay. I'll write x as x hat XOR d, all right, where d is basically Bernoulli, I'm sorry, let me call this z, where this z is a Bernoulli d random variable. Okay. So one thing that I'm assuming over here is that d is greater than p. All right. I want you to think about what happens when d is less than p. Can you say something about this particular quantity if d is strictly less than or equal to p? Okay, and the assumption is that x hat and z are independent, z is Bernoulli d, x is Bernoulli p. So this is another homework. So in this case, x hat is also Bernoulli because it's binary. It's Bernoulli q, find q. For what parameter q are you going to get? So remember that we fixed we have fixed the distribution of z, we have fixed the distribution of x. What I'm asking you to do is find the distribution of x hat, assuming that x hat and z are independent of each other. They're not identically distributed, but they're independent of each other. Okay, so if this is the case, if this is the joint distribution, then what is the mutual information? So first, what is expected value of d xx hat? So in this case, when is x going to be equal to x hat? When z is equal to 0, right? So x is equal to x hat if and only if z is equal to 0, and it is going to be not equal to x hat if z is equal to 1. So the expectation of d of xx hat is basically the probability that z is equal to 1, which is it's equal to x. Yeah, it's a probability that x is not equal to x hat, but what is the probability of z equal to 1 equal to? It's d, right? So great, this satisfies the constraint of our rate distortion function, right? So what is the mutual information between x and x hat? What is the second quantity going to be equal to? What is the entropy of x hat XOR z given x hat? It's going to be equal to the entropy of z, right? I want you to prove it if you're not convinced. All right, try to expand because everything is binary. All right, x hat and z are binary, and x hat and z are independent of each other. You can show that this is equal to the entropy of z. So this is equal to, what is x? It's Bernoulli p. So this is the binary entropy of p minus the entropy of z. Z is Bernoulli d. So this is equal to H2 of t. Right? So for this we chose one particular distribution, right? One particular p x hat given x, and showed that the mutual information is equal to H2 of p minus H2 of t, which means that our star of d is greater than or equal to H2 of p minus H2 of t, because the rate distortion function is obtained by minimizing over all possible conditional distributions p x hat given x. We got this by choosing one particular distribution p x hat given x. what we want to show is that this, in fact, this conditional distribution minimizes the mutual information. So let's look at this mutual information between x and x hat. This is equal to right. So this is equal to h of x minus h of x given x hat. What I want to do is show that this quantity, so let's define say the random variable e, which is equal to 1 if x is not equal to x hat. It's equal to 0 if x is equal to x hat. All right. What is h of e going to be equal to? So what is the probability that e is equal to 1? It's the probability that x is not equal to x hat, which is exactly d by definition, right? So h of e is just going to be, so e is basically a Bernoulli d random variable. All right. So h of e is going to be equal to the binary entropy of d. And our goal is to show that this mutual information is always less than or equal to h of x minus the binary h of e, essentially. That's what our goal will be. All right. Want to show that this is greater than or equal to h of x minus h of d for all p x hat given x. So let's look at h of x given x hat. This is less than or equal to h of x of x and right? In fact, it's equal to h of x hat given x hat. So it's nothing but just a dummy variable I'm including in. All right. Now this is equal to h of x hat e given x hat. Why is this true? So basically I'm going from this step here to this step here.
E is a deterministic function of x hat.
Okay, is that just enough? So a little more than that, you're close. Basically, there's a bijection between x hat and x hat e. Right? If I tell you the value of x hat and e, then you know the values of both x and x hat, and vice versa. And you know that the entropy is invariant to bijections. So this is equal to h of e given x hat plus h of x hat given e and x hat, which is equal to 0. So h of x, okay, maybe one more step, but this quantity is also less than or equal to h of e. It's equal to this. It's equal to h of x hat given x hat plus this, right? So it's in fact an equality. It's also an inequality. That's all. I guess I could just say that this is equal to So finally I have h of e given x hat is less than or equal to h of e, because conditioning can only reduce the entropy. So the mutual information between x and x hat, which is h of x minus h of x given x hat, is greater than or equal to h of x minus h of e, which is equal to the binary entropy of P minus the binary entropy of D. And this is true for all conditional distributions P x hat given x, for which the probability that x is not equal to x hat is equal to D. So this, both these put together show that R star of D is equal to the binary entropy of P minus the binary entropy of D. Alright. Any questions? So I'll also leave it as an exercise. So try to show this using Lagrange multipliers. Alright, try to set up, you have the constraint optimization problem. Define the Lagrangian and using Lagrange multipliers try to solve this optimization problem. The nice thing is that this is a convex optimization problem. So you can solve this using Lagrange multipliers, but in many cases it is not very easy. It can get much more complicated. In this case it's easy because there are very few parameters involved. When you're looking at more general distributions, it becomes harder. More so, for example, if you look at continuous sources. Because there the number of variables involved is not finite. In this case, there's only one variable, p x hat given x, effectively just involves one variable. And you only have to do the minimization with respect to that single variable. When you want to solve an optimization problem of this form, right, an optimization problem of this form, f x hat given x is a density, it's a function, right? So you can't just use Lagrange multipliers to solve this. All right. Any questions? Okay, so if not, let's stop here.